One of the most important words chemists use is the word substance. A substance refers to different types of matter. When we look on a more advanced scale, we have the pure substance. For a material to be considered a pure substance, it must satisfy two properties. One, it must have reasonably definite chemical composition, and two, it must be a homogeneous species of matter. Pure water and pure salt, for instance, are both pure substances because they have reasonably definite chemical composition and they also are a homogeneous species of matter. Since they satisfy this, they are considered a pure substance. To learn more about general chemistry and to understand the essence of pure substances, continue watching to the end of this video. Hi everyone, today I'm going to be talking about general chemistry. So what is chemistry? Chemistry is the study of reactions, properties, and behaviors on the molecular scale. Now what do we mean by the molecular scale? Now in physics we talk about the subatomic realm or the subatomic scale, which just means smaller than the atom. And we talk about the atom too, just on the atomic scale. Now chemistry is essentially built upon the atomic scale and the molecular scale. So we have atoms and molecules. These are essentially where chemistry operates on. These are where the specific types of scales the chemistry operates on, and kind of like axioms in mathematics. So that's essentially what chemistry operates on atoms and molecules. Now chemistry answers questions like, what happens if we mix this and this? Why do these react like this? What are the properties of this? Now chemistry answers these big questions, but also small questions too. Like what are the atomic mass of this? What is like the chemical properties of this? What happens if we react to, what happens if we add this amount of iron or magnesium to something? So it essentially just answers the big questions and also answers the small questions. And it answers them on the molecular scale and the atomic scale. Now chemistry has a lot of relationships with biology and physics. For example, in nuclear physics, we have radiation, which is also a part of chemistry. Now when we look at biology, we have biochemistry, which combines both chemistry and biology. One of the most fundamental equations in physics that revolutionized chemistry is E equals mc squared. It told us that light also has mass, which is very important. It also revolutionized chemistry in many other ways. Chemistry has also revolutionized physics. For example, there's a new field called quantum chemistry. It combines quantum mechanics and physics and also chemistry. So that's a new field, quantum chemistry. Okay, so let's begin by talking about two of the most basic words used in chemistry. As mentioned previously, we have substance and material. Now material just refers to matter, so when we're talking about a specific type of matter or just any type of matter in general, or just referring to the broad term matter, we can use the word material. So substance refers to different types of matter, like a specific type of matter that we consider. That's referring to a substance. So material just refers to matter in general, and a substance refers to a specific type of matter. Now, we will be talking about pure substances later, but before that, we have to talk about the IS or SI units which are used. Now, IS or SI are both the same thing. Now, IS is just the International System units. So that's what IS is. So IS units are used, and it can also be called SI. Now, in chemistry, units are very important because we're dealing with lots of numerical values. So units are very important. Now, there are multiple aspects of the IS or SI system. Now, we will be talking about one of the aspects today, temperature. So Celsius or centigrade was developed by André Celsius in 1742. Now, André Celsius was a Swedish professor of astronomy. Now, negative 273.15 degrees Celsius is the minimum point of temperature, or absolute zero. Now, theoretically, in terms of theory and mathematics, temperature can go on a scale of infinity. We could have -1, -2, -1,000,000, -1,000,000,000,000 on a mathematical scale. But on a physical scale, we have to actually talk about the minimum point of temperature. This doesn't make any sense in reality as we know it because we perceive reality to be simple, but it actually does have a minimum point of temperature. And this is called absolute zero. And this also has an intricate relationship with physics. Now, temperature is also an important subject used in physics. So, in temperature, there was first the caloric theory, which essentially describes particles for heat. But we now know that the chaotic theory is false. Instead, we have the theory that essentially when we have heat, essentially the particles in a specific type of material we're studying move faster. So if we're considering that water heats up, that means the particles are moving faster. If it's colder, the particles are moving slower. Now, in a physical point, we can say that when the particles are moving slower and slower and slower, they can essentially stop to a specific point. It's kind of taking like the limit in calculus. So they stop to a specific point. So when the atoms stop, like purely stop moving at a specific point, that is called absolute zero, or the minimum point of temperature. Now, Lord Kelvin invented the Kelvin scale. Now, the Kelvin scale is closely related with thermodynamics, because thermodynamics and the Kelvin scale are created accurately so that they can both accommodate each other. And Lord Kelvin also did a lot of research in thermodynamics. Now, absolute zero in the Kelvin scale is 0 degrees Kelvin, which makes perfect sense because the name absolute zero fits it. And the freezing point of water is 273.15 degrees Kelvin. So it's always 273.15 degrees greater than the centigrade. Now, we can actually test this. For example, if we're stating that negative 273.15 degrees Celsius is equal to absolute zero, then we're saying that this will 0 degrees Kelvin. Then to get to essentially 0 degrees Celsius, we're adding 273.15 degrees Celsius. So we 273.15 degrees Kelvin. When we add it to here, it just cancels out to zero. So 0 degrees Celsius is equal to 273.15 degrees Kelvin. And 0 degrees Celsius is obviously the freezing point of water. So at the Kelvin scale, it's always 273.15 degrees greater than the Celsius scale. Now, this is one of the most important aspects of the SI or IS units because Kelvins are used a lot. Now, Celsius is also used a lot in science, but Kelvins are also used when we're dealing with extreme temperatures and so on and so forth. Okay, now let's actually talk about some of the most important definitions inside the substances and materials. Okay, so you have to first talk about homogeneous and heterogeneous properties. Now, homogeneous just means we have the same properties throughout, and heterogeneous just means we have different properties. Now, what does this mean to us? So if we have a homogeneous material, when we're saying that material refers to matter in general, if we have a homogeneous material, we're stating that we can essentially, knowing one part of this specific type of material, we can essentially describe the properties throughout all of the parts of the material because they have the same properties throughout. This is one of the most important definitions in chemistry, which we'll see a lot. Now, when we're looking at heterogeneous, this means we have different properties. They don't have the same properties throughout. Oh, thank you to the book General Chemistry by Linus Pauling for the definitions used in this video. Okay, so homogeneous just means the same properties throughout, and heterogeneous just means different properties throughout. For example, we can have a solution in a mixture. So solutions and mixtures are very important. Now, a mixture has a specific type of definition, which we'll talk about in the next video. But in general, mixture is just when we're combining multiple things together. And solutions, those multiple things, but more dissolved. Now, there's a more technical definition involving homogeneous and heterogeneous, but we'll talk about that a little bit later. Okay, now let's talk about the pure substance. So the pure substance has definite chemical composition and is a homogeneous species of matter. And reasonably definite chemical composition. Now, what does the definite chemical composition mean? So let's consider a counterexample. So say we have this glass of water. And we add some sugar to it. So we add some sugar into it. Now, when we add this sugar into the water and we completely dissolve it, this is going to be a homogeneous species of matter. They pretty much relatively have the same properties throughout. But the chemical composition is what is the main thing here. Because the chemical composition seeks that the material has to be composed by reasonably the same chemicals. But But this is determined by the amount of sugar. Sugar dissolved. Because if we add more sugar, we have more sugar dissolved in the water. So a little bit more, one could say, reasonably definite chemical composition. So that's why the variable here is the amount of sugar. And in general, we're not supposed to have any variable terms right now over here at the definition. Now, when we talk about salt, for example, salt is a pure substance. So we'll define this to be salt. Now, salt is a pure substance because, one, it has definite chemical composition, and it's a homogeneous species of matter. Notice that when we're talking about homogeneous species of matter, we just mean that it's a homogeneous matter, same properties throughout. Now, you might be wondering, how does sugar water have the same properties throughout? Well, if we consider this specific type of chemical equations and things we'll learn in the future, chemical properties of this type of the material, or sugar water, for example, we're considering, they're going to be the same throughout the whole glass of water. Now, when we're considering salt, for example, just plain salt, this is just sodium and chlorine combined. Now, sodium and chlorine combined gives us salt. And when we just have regular salt, for example, table salt, this has sodium and chlorine combined. So each of the atom has sodium and chlorine. So this is going to be salt, and it has reasonably definite chemical composition. And since it has sodium and chlorine all over, and it's just salt, it has the same properties throughout, which is the homogeneous species of matter. Now, water, as I mentioned, is also a pure substance, because water, for example, with nothing dissolved into it, is a homogeneous species of matter. This is a good example for homogeneous, because no matter if you take water and you take any glass of water or something with nothing dissolved into it, so if we take pure water, any pure water, we see it has a freezing point of 273.15 degrees Kelvin, or moreover 0 degrees Celsius, or 32 degrees Fahrenheit. Now, if we have 32 degrees Fahrenheit, 0 degrees Celsius, or 273.15 degrees Kelvin freezing point, that's a property of water, and it maintains the same. So water has the same properties throughout. So that's homogeneous. And also the definite chemical composition. We have H2O. This is definite chemical composition for the water in the glass. So this is essentially pure substance. Now, when we're talking about pure substances that satisfy these two properties, we will mention the word pure. But when we're just talking about a regular substance, just referring to a specific type of matter, we will be talking about just the word substance. Okay. Now let's talk about a mineral. So a mineral is any chemical element, compound, or homogeneous material occurring naturally as a product of inorganic processes, such as water or mercury. Now, let's decode this definition. So, a mineral is any chemical element, that's pretty straightforward, compound, or any homogeneous material. We talked about homogeneous meaning same properties throughout the material, referring to matter. Now, a mineral is just not a homogeneous material. It has to occur naturally as a product of inorganic processes. So if it occurs naturally in nature as a product of inorganic processes, then, and it satisfies one of these, either this, or this, then it will be considered a mineral. So if it's a chemical element, a compound, or homogeneous material, saying that it's a matter that has same properties throughout, and occurs naturally in nature as a product of inorganic processes, then it's considered a mineral. That's what a mineral is. So if we take a mineral, for our definitions right now, by what we've learned so far, we'll consider a mineral just to be a homogeneous material. Now, a mineral can be a chemical element and chemical compound, but if we just consider it to be homogeneous material, we're saying that it's a homogeneous material that occurs naturally as a product of inorganic processes. So this homogeneous material should occur naturally by essentially inorganic processes. And that's pretty straightforward. A type of matter with the same properties throughout that occurs naturally by inorganic processes is a mineral. And that's pretty much the basic definition of a mineral. Now, in chemistry, we're dealing with a lot of units. And as I mentioned, the specialty of one of the equations, E equals mc squared, is very important. So let's just talk about E equals mc squared a little bit, and then talk a little bit more about how this works in chemistry. So E is the energy, m is mass, and t is the speed of light. Now, when Einstein came and created the general theory of relativity in physics and special theory of relativity, he introduced E equals mc squared, which relates the energy to the mass. Now, this is very important because we consider the difference between mass energy and radiant energy to be that if we consider, let's say, an object, let's say a ball. Now, this ball, for example, has to have a specific mass. And it has energy, because this equation implies that anything with mass has energy, and anything with energy has mass. Now, at the time when we considered radiant energy, we just thought of light, which is just radiant energy, to literally have no mass. Since light, which is radiant energy, we thought to have no mass, this kind of revolutionized our study of radiant energy and normal at things with mass. So when we thought of something with mass, we didn't think of light. We just thought it has mass. But when Einstein came up with this equation and also did general relativity, we realized that light also has mass. And sometimes it's just negligible because it's very small. Now, moreover, light, for example, is attracted by a black hole, by the gravitational pull. Now, for example, gravity, it pulls on things which are mass, and this kind of implies that light has mass too. So as you can see, radiant energy equals mc squared, and the energy of an object all relate together, and it kind of shows how light also has mass. Now, you might be wondering, this is physics, how does this relate to chemistry? In chemistry, we study a lot of numerical values. Not just numerical values, we study equations too, but a lot of numerical values. For example, the atomic mass and so on and so forth. The energy is one of the most specific types of things. For example, in radiation, energy is It's very important too. So energy is also very important. In the next video, we'll talk about mixtures, solutions, phases, and a little bit more on general chemistry. If you like this video, if you like this channel, please subscribe to learn more. Thank you.